Okay. All right, guys. Let's do a quick overview of what we covered before we left for break. So basically, this is the ground. This is going to be a super fast overview. So if this is the ground so if an object is up in the air, if it has some kind of height, and let's say it's moving with some velocity, so it could be moving, the velocity could be in any direction, it could be moving down, it could be moving up, it doesn't really matter. So say it has some velocity vector v, and it's got some mass m, so you can describe its energy. So as we're going to as hopefully you'll understand over the course of the next couple of weeks, energy is like this sort of this quantity that tends to get conserved. It's just it's hard to describe really. It's hard to really sum up what exactly is energy in one sentence, but it's like this quantity that sort of gets transferred around and conserved as a system evolves. So anyway, so you have kinetic energy. So this kinetic energy would be 1/2 m times v squared. And so you get results like, say, if you double the velocity of your object, what happens to the kinetic energy? 4 times bigger. Okay. If you double the mass, it only doubles the energy. Okay. So it's nonlinear relationship with V. And then so you've also got potential energy. Let me use an uppercase U for, which is m times g times h, where g is just your 9.8 meters per second squared. And so what you would say for this guy is the total energy would just be the sum of those. You'd say, oh, this thing's moving through space here, it's got kinetic energy and it's got potential energy. So the total energy of the system would then, now so if the thing, let's say the thing, say loses some height, right? If h gets smaller, right, what happens to this term over here if this one gets smaller? This one would have to get bigger because a big sentence that we'll say a lot is the energy is conserved, which just means it stays the same. So if this system had, say the total energy was 100 joules, well, a second later, the energy is still going to be 100 joules. And a second later, it'll still be 100 joules. Now, until something happens, so if you start to throw in say friction or say it hits the ground, what happens to the energy if something, here, right? Oh, it had all that energy. Now it's got no energy. Where'd the energy go? It was converted into sound mostly. Maybe a little bit of heat there when the thing hit the table. That kinetic energy, it's potential energy, converts to kinetic energy. And then once it hits something, that energy is converted into heat and sound mostly. Okay, and then what else? So that's an overview of kinetic and potential energy. Then you might wonder, where did that energy come from? Usually it's work. So maybe you're like, well, how did the ball get up there? Maybe someone threw it. Maybe it shot out of a cannon. Whatever. There's this work energy theorem, which is if you do work on an object, that's equal to the change in the total energy. So that's a big theorem in physics. Again, so if you have some system, you go, oh, the system used to have 100 joules of energy, and now it's got 120 joules of energy. Well, how did it get extra energy? Well, someone must have done 20 joules of work on it, on the system. And then work is force multiplied by distance. All right, that's a super fast crash course and everything, I think. I guess I forgot one thing, which is the last thing we covered before the break was the graphs, right? On the problem set, at least that's the last thing we did. So if you have a force versus displacement graph, something like that, and the graph, whatever it is, a lot of times it'll look something like this. How do you find the total work Well, it's the area. So if you connect this all together, you can do these problems where it's like, oh, how? Let's start with. Can we ever do 15? I guess not.
Nope.
Okay, let's look at 15 together then. So 15 will kind of tie in everything except for this. It's all about kinetic energy. All right, let's read it. A 200 kilogram block is initially at rest on a frictionless surface and connected to a rope which pulls the block a distance of 6 meters in one direction. So you can see on the graph, you see the distance on the distance axis, it goes 6 meters. And then the y-axis tells you how much force was exerted on the block during that process. And it was a frictionless surface, so you know that there was nothing opposing that force. Okay, so go ahead and calculate the area, because the area under the curve is going to tell us the total work done on the object. So part A is just kind of a geometry question. It's a trapezoid, but unless you really are keen on using the trapezoid formula, I would recommend just breaking it up into 2 triangles and a rectangle. This is 30. And so the areas involved would be, what's the first triangle? 45 in there, right? So this first triangle of area represents 45 joules of work. Does that make sense? Yes. No questions on that, right? Okay, so 45 joules. So newtons, this is newtons, this is meters. Newtons multiplied by meters gives you joules. And then this next piece would be 2 times 30, which is 60. So then you add 60 joules. And the last one is 1 times 30 divided by 2 is 15. And so you add that all up, you get 120 joules. So before we move on, are there any questions? It's pretty straightforward, right? Okay, and then it says, what's the block's final velocity? This question, it's not really obvious that this is the case, but this shows you the how useful the concept of energy is, because this would be extremely annoying and difficult kinematics problem if you had to do this purely with F equals ma. But if you use this idea, the work energy theorem, and then you combine that with how we quantify kinetic energy, it's going to be a really easy calculation. So it's very useful. When you're talking about energy, it's very nice to be able to say, well, I have a starting condition and an ending condition. I can connect those mathematically with energy. So, okay, so this problem, we just calculated the work. So the work that we just calculated was 120. And what's the thing started off with no energy, and it ended up with 1/2, what's the m, 200? mv squared. Make sense? So I replaced this with that.
Good morning. We're Mr. Hall. Is Julia here?
Which one?
Julia Martin, sorry.
Julia Martin. They're both here. Okay, so then solving this is fairly straightforward. You divide by 100. So you're gonna get 1 point, I don't know, whatever, what's gonna end up when you get there, 1.1 or something. Anyone out there? Anyone?
It's 1.0954.
Okay. So are we cool with that? Yes.
Is it okay if I round it up to 1.1? Or do you want me to keep it?
No, that's fine. As long as the work is shown, the final answer isn't that critical. Where are you around it? Okay, so help me out here. Did we do 16 before we left or no?
No.
Okay, good. You're gonna do 16 because it's, oh my goodness, it's a full page. It's a 6-part question. Dun, dun, dun. So this will hopefully cover the whole kit and caboodle as far as kinetic and potential energy, how that all. Did I not do my thing? I thought it's, I know I did my thing. I must have. Hello. Oh, okay. No problem. See you. Colin. You out of here.
And he's gone.
You gone. Your return was so short-lived.
I'm going to order the dawn.
Oh, okay.
I would fail if I got this. I'm already pretty much. I would really not be good if I got
Okay. So 16, 6-part question. A cannonball is fired straight up from ground level with an initial velocity of 30 meters per second. So we're going to sort of draw the here's the cannon. Okay, so right as it leaves the barrel of the cannon, the mass is obviously 10 kilograms. The velocity, this is the initial velocity, is 30. Okay, so what's the initial, let's calculate that. Initial kinetic, so kinetic initial, a little naught next to it, would be 1/2 mass times velocity squared. So 900 times 5. I think that's right. That makes sense to everyone? What's the potential energy if your height is 0? 0. Are there any questions on that? So right now, what's the total energy of the system? 4,500 joules. If you want to think more broadly, where did those joules come from? Where did that 4,500 joules come from?
Well,
Yes. The explosion, right? There was chemical, for you chemists out there, there was chemical energy stored in the gunpowder or whatever was the propellant for this thing. If it was an old-fashioned cannonball, it would be in the gunpowder, right? So the gunpowder had chemical energy. When it was ignited, a chain reaction happened, and all that chemical energy was converted through an expanding gas, right? That expanding gas did work on the ball and gave its energy to the ball. Okay? Part B, what happens to the cannonball's kinetic energy as it travels upward?
decreases, but your potential increases.
Yes, so to you, yes, that's exactly correct. The kinetic energy will decrease while the potential energy increases. But a better way of saying that is probably to say the kinetic energy is converted into potential energies. So like in physics and engineering, they're a lot of times talking about, they're talking about this nebulous concept of energy and how it's kind of transferring between these different, it's like, where's the energy? Oh, maybe it used to be in the gunpowder. Now it's in the movement of the ball. And then as it travels upward, it's transferred into the potential energy stored in the gravitational field. Need some soda pops, Kate? No. You need a 3-shot caramel unicorn macchiato.
So then Mr. Hall, full circle on this, then when you're kinetic energy is at 0, then your use would be at 4,500 joules because it's at the max height
Yes.
and the transfer wind capacity.
Very good. Exactly. So this ball, this connects back to kinematics, of course, because remember in kinematics we talked about how if this ball reaches its max height, so let's say this is the max height. Well, at the max height, what's your velocity? Unless you're, well, if it's, assuming it's traveling perfectly vertically. If we're traveling at an angle, then you'd say the y component was 0. But anyway, the max height velocity is 0, so the kinetic energy is 0, which means that logically, where'd the energy go? Well, it must have gone into potential energy. And then, so part D is how do you find what this max height actually is? Well, you know the potential energy quantity, and you know a formula for potential energy. So let's set those equal. You go mgh equal 4,500. Okay. The mass we know is 10. G is 9.8. Okay. And so you're going to get 40 something, I don't know, 46-ish. Did you get a number, Kate?
45.92.
Let's call this H max, sorry. H max. So you guys might recall, like, if you're having like deja vu, like, wait, didn't we do a problem before where you found the max height of like a cannonball or some, just any projectile? When we knew the initial velocity, we found the max height. Yeah, so we did do that with kinematics. This is a lot more straightforward, I think, and it's also neat. I think it's interesting because it shows that, well, it kind of reinforces the idea that this whole energy concept does make sense and fits in logically with like movement and force and all that stuff. Because we actually solved a problem just like this before we actually even talked about force at all. It was purely kinematics. Okay, now in part E, what happens to the cannonball's potential energy as it travels back toward the ground? It's like a converse of what we had before, right? It's now that this is all potential energy, and it's getting transferred back into kinetic energy as it travels down. So H goes down, V goes up. And then how do we figure out the cannonballs? Well, F is kind of interesting. Who knows the answer to F? What's the velocity as it comes down? Anyone? Yeah. If in a perfect world with no air resistance, it would just be 30, just by symmetry. But let's say we're like, I don't know. I really like energy. I'm going to solve this using energy. Well, that's fine. Okay, right. Down here, the potential energy is 0. The kinetic energy is back to that 4,500 joules. And so if you go 1/2 mv squared equals 4,500, you might notice, wait, aren't I just solving the exact same equation from before? So wouldn't V have to be 30? Yes, it would. You can confirm for yourself if you plug in the mass again was 10. Running out of room. But of course, like you said, a little bit less than 30, right? It would depend on the object. If it was like say a soccer ball, or maybe a better example is a beach ball. If you bop a beach ball as hard as you can right into someone's face, doesn't feel very good, or say a regular volleyball, whatever ball you want to think about. But if you hit it way up into the air and then let it come down and it hits them, it's not going to hurt as bad. And that's because if you have air, there's a whole bunch of air molecules in here. Then what happens is the ball, as it goes up and as it comes down, transfers some of its energy into the kinetic energy of the air. Because every time it bonks into an air molecule, it imparts some of its, we'll talk about momentum soon, but it gives up some of its energy / momentum to the air molecules around it. And so macroscopically speaking, you'd say, oh, the air as a whole is kind of sapping away the energy of the cannonballs. Okay. Are there any questions at all? I haven't had any yet, so does that all make sense? All feels good? Okay. So, I think that's about all I got to cover as far as 17 through 21 are very similar to that. I guess I do want to go over maybe one more example where 20, yeah, I want to do 21, which will be like similar, yeah, and it'll be similar to 27, but let's just do 21 together. This will be the last one that I want to cover for a little while. Tomorrow we can, I know there's full disclosure, hopefully by the end of this, I know it's like 60 problems, close to 70, actually it is 70. Hopefully you'll be like, okay, I get it. Like, geez, enough with kinetic and potential energy. But it's such an important concept that I wanted to give you guys. At least as something that I can be sure there's enough practice that you get how straightforward it is. So anyway, so 21. Here's the main idea for 21. So this says a cannon is mounted on a platform 20 meters above the ground and pointed straight up. So here's the ground. Here's the platform. 20 meters. So the question's asking if we know how fast the ball is shot out of the cannon. So this is V naught. How do we calculate the max height, and how do you calculate how fast it's going to go? So it's going to go up. It's going to hit a certain max height, and then it's going to come all the way down. Assume it's offset just barely enough so it doesn't come back and hit the platform. It hits the ground instead of the platform. So first, basic question. When it hits the ground here, will it be going faster or slower than 30 meters per second? Faster. Now the interesting part is, do you think it'll be going way faster? Would a reasonable answer be like 45 meters per second or maybe like 32 meters per second? That's a question that we'll see the answer to it pretty quickly. The 3 was messed up. So some food for thought here is, this thing's going to come up in the air, right? When it comes back down, when it passes by the platform, how fast will it be going? 30. So how much time is it going to spend traveling that last 20 meters?
Less than a second.
Less than a second, yeah. So it's not going to spend very much time accelerating there. So you can expect the answer is going to be not like maybe 33, 34 meters per second. Not very, all I'm saying is it's not going to be like, don't expect this to be like 70 meters per second, okay? Okay, so anyway, let's get the calculation. So totally just energy. What's the total energy right here? Let's just use the letter E for energy. Total energy, or E initial, how about that? The total energy would be, he's got potential, right? So he's going to have, what was the mass? 6. So 6 times 9.8 times 20. So there's his MGH. Plus 1/2 times 6 times 30 squared. Let's get his total energy. By the way, is anyone thinking right now, wait, couldn't I just ignore the 20, figure out the max height, and then add 20 onto it? Is anyone thinking that maybe? That's correct for finding the max height. But I want to show how we can just use the same total energy to solve for this and this. So if you're thinking that, like you're thinking correctly. Yeah. So this is our 1/2 mv squared. Is anyone able to calculate that for us? What would that end up being?
3176.
Sounds reasonable to me. Can anyone confirm that? So this number is going to be very helpful for us. Well, let's roll with it. We'll trust you, Aiden.
That's fine.
You confirm?
Mhm.
Okay, Kate confirms. Good. Okay, so now let's look at the final. Well, there's 2 finals to consider. Let's look up here. So energy up here. Does he have any kinetic energy up there? Because up here his velocity is 0, right? So if your velocity is 0, then your total energy is just mgh plus no kinetic energy, right? So what can I do to find the height? I can just set mgh equal to this total energy amount. Does that make sense why I can set those equal? So to get that top thing, I would just write mgh equals the total energy, 3867. Let's call this H max, I guess. H max. Now what do we get for H max? Oh, great, Quackalator. What say thee? 65 something? Okay. All right, so what you would have found if you had been like, oh, I'm just going to ignore the 20, calculate this max height as if he came off the ground, and then add 20 onto it, that's exactly what you would have got. In fact, I think the question we just did earlier was 45.9, wasn't it? 20 meters. So anyway, so now we're going to say, well, okay, it's now fall. Let's figure out what's the velocity. So down here, he's all kinetic energy now, no potential energy anymore. So I can write 1/2 mv squared, set it equal to the total energy. Does everyone understand why I can write this one? Why this is a valid equation?
Yes.
So 3876 divided by 3, the square root, you get about 35.9. So a little bit bigger than I said earlier, but I guess my point was still stands that it wasn't like way bigger than 30. Only about 20% larger than 30. Are there any questions on step 1, step 2, or step 3? So yeah, the moral of the story is, yeah, if you can calculate the total energy of the system, you can then go to any point later on in the problem and say, well, I'm just going to set the total energy equal to this number and just calculate whatever I'm looking for. So, okay. Let's just end the stream here.